Alright, we're going to try to finish up one last video for tonight, and that's going to be the common base amplifier, and that should get us through all of our transistor amplifiers, at least for the BJTs. Now, the common base amplifier is given here. It looks quite funky compared to what we've just looked at, but it's a similar procedure like we did for the previous videos. So we know that we need to do some DC and AC analysis, and we need to know the DC analysis first, because that allows us to find our DC base current, and that is going to help us find our R pi value, which helps in the AC analysis case. Now, if all of these capacitors are relatively large, we say that the impedance of them is approximately equal to 0, and if any of this seems like it's gone through pretty quick, please check out the last few videos. We go into this and then we speed things up. And then typically we want to find some voltage gain, some input impedance, and some output impedance. So from the DC analysis, the first thing that we're going to do is set our AC source equal to 0, and we're going to set our capacitors to be open circuits. So now our amplifier looks something like this, or we can simplify it up to look like this. Now if we moved R2 into a vertical orientation and connected ground, what would we have here? Well, if you entered the 4 resistor bias circuit that we've looked at a few times now, you're correct. So what we can do is use our pseudo source transform. Again, we've gone through this many times in the past to arrive at a circuit that looks like this, and this is going to allow us to make a KVL around this base loop. Now once we do this, we get this ugly looking equation again, but that's okay because if we know all of our values, we can calculate what that DC base current is. Now from knowing that, we can find R pi, because we know what VT is. That's the thermal voltage, which is 26 millivolts at 300 degrees Kelvin, or about room temperature. So now that we found R pi, what we can do is go into our AC analysis. So we set those DC sources, or in this case, the singular DC source equal to 0, and our capacitors are shorted. So now we have a circuit that looks like this, for which we're going to swap out the BJT model with our small signal model. Notice here, we're using that R pi value that we found from the DC analysis. So plugging that in, we end up with a circuit that looks like this. Again, still doesn't look too nice. Now, if we look at the output voltage, which we have right here, where that other reference point is to ground, we can see that this current has to be the current flowing through the parallel combination of RC and RL. So we can say that the output voltage is equal to minus beta times IB times that parallel combination. Now, the input voltage, well, you can see here that Vin is going to be the voltage over RE, which we can also trace back to be the voltage over R pi. Now, because of the way that we denoted the base current, what we get is that the input voltage is equal to minus IB times R pi. So now we have our output voltage and our input voltage. We can find our voltage gain simply by that ratio, and that's going to be equal to beta times the parallel combination of RC and RL divided by R pi. Now, typically in this amplifier configuration, our voltage gain is pretty high. But to move on to find the output impedance, we know that what we want to do is remove the load resistor RL. We're going to set our source voltage equal to 0. And then we're going to look into the terminals from where RL was, and that should give us our output impedance. So if we set this voltage source equal to 0, we essentially have RS, RE, and R pi in parallel. By looking into the terminals, we really only see RC. So that's going to be our output impedance. Now for the input impedance, we are looking at the input voltage divided by the input current, and our input voltage is again right here. So if we set up a KCL at point E, we're going to say that the base current plus beta IB times the base current plus some input current, that's going to be equal to the current that's going through IRE. And we know that the current through IRE, that's going to be equal to the voltage Vn divided by RE. So that's pretty straightforward. So we can simplify this and say that the input current plus beta plus 1 times IB, that's going to be equal to Vn divided by RE. And again, because we labeled the base current like this, we can say that IB is equal to minus VE, or the emitter voltage, divided by R pi. And that's also going to be equal to Vn, or minus Vn divided by R pi. So we can substitute this in from what we had above. That's going to give us our input current is equal to Vn times this term here. And from that, we can simply divide Vn, or the input voltage, by the input current to get this term right here. And that's going to be our input impedance. Now again, if we simulate this, so in the green here, we have a very small input signal, and in the blue, we have our output signal, and we're looking at the voltages. And you can just graphically see here that the gain between the output and the input is pretty massive, which matches what we predicted above, where we said that the gain is pretty high. And notice here that the overall gain in the system is pretty dependent on the beta value. Now typically our pi might not be that big, maybe a few thousand ohms or 1,000 ohms, but if we have beta and then this parallel combination of RC and RL, depending how we size those, that's where we can get that gain to be pretty big. Now this will cover all of the basic amplifiers for NPN BJTs. In the advanced electronics course, we're going to look at a lot more amplifiers and a lot more details about the amplifier systems. We have one more video where we are actually going to look at how we can create logic gates from NPN transistors or PNP transistors. You'll have to wait and see. But this will tie back to one of our introductory courses, which was the logic course. So now we're starting to see how we can use electronics to build other component blocks that we used in previous courses. If you learned anything useful, please like, share, comment, subscribe. Helps out the YouTube algorithm, and we'll see you in the next video.